Federal Rural do Rio de Janeiro, que vai falar sobre stiff balance laws and parallel computation with implicit discretization. A tradução em português está lá.
Well, I prepared the slides in Portuguese, but since there is an audience that speaks only English, I will present in English. Okay. Well, this is a problem that I will treat that was brought to me by Dan. That's the title maybe is not quite well clear, but I mainly will speak about some how a way of make parallel computations for implicit discretizations of balance laws. And one problem is the balance laws with the stiff terms. The general problem is a balance law. Balance laws can have k variables, and therefore we have k balance laws in a 1D domain. You can use Crank-Nichols discretizations to solve this implicitly using a Newton method to solve the nonlinear system. Usually with this discretization you get a system that is tridiagonal by blocks. It's a block tridiagonal with a k per k blocks. Then we will present a way to make parallelization of this kind of systems. One problem that we get to test the solver was another equation with relaxation term. This was presented by Abel in a poster, and was brought to me by Wanderson Lambert from the same university, so that we could get a system with 3 by 3 blocks. But we would like to use this kind of simulations to solve problems with more terms, more equations, like 7, 8 equations. That's a problem that I started working with Dan and Alexei. That comes from models with combustion waves. So we will present first the main ingredient of the solver to parallelize the problem. It's a well-known technique that's called Schur complements, where you have a linear system. You partition the matrix A like this, B, C, D, E, where B and E are square matrices. Okay, you assume that B and E are the linear system associated, have solution. But for the first equation, you get bx1, cx2 equals b1. You can eliminate that x1 and get b minus 1, b1 minus cx2. You get this x1, substitute in the second equation, and get a linear system with only x2. Okay, this is the well-known Schur complement method. Once you solve x2, you go back here and solve x1. You get a beneficial of this. For the problem we will show, you will get parallelization. But this system, you get another thing that's a better condition of the linear system, the resulting linear systems. You get, therefore, better numerical stability, since you get a better condition. And as an example, if you make a discretization of Laplace equation with finite elements or other kind of of method, you get a condition that's order 1 over h squared. It's a well-known result. That's the condition of the system is 1 over h squared. But if you apply sure complement, you get order 1 over h. It's a much better condition, so you get better stability, numerical stability. This problem was treated in a dissertation thesis by Gustavo Rime. And we are revisiting this problem, and we hope to improve also some kind of things there, such as using a Gemini res on other in the inner linear systems. But it's a work that we are about to work in the future. Let's go to the proposed method. Consider that you have a matrix that's block 3 diagonal. You have 3 diagonal blocks. You partition this matrix like in P submatrix A1, A2, A3 up to AP, and leave in the between smaller submatrices. These AI are submatrices that MI K blocks. Okay, this matrix A1, A2, and so forth, they are bigger matrices, but these lambda 1 are K per K subblocks, a single block only. Okay, then you have a partitioned system where you have x1 that's KMI and xi that's are K variables. We choose MI, that's the size of the division, so that you get approximately the same size of A1, A2, and so forth, so that you have a balanced computational costs. This matrix Wi, phi, gamma I, theta I, since the matrix 3 diagonal, they are some structure. This matrix theta I, this other matrix, they are a lot of zeros. This part is 0, this part is 0, this part is 0, and this part is 0. This part, gamma IC, is a K per K, a full K per K matrix. This also is one full, and full matrix. This structure also is beneficial for the problem because in the implementation you get some little beneficial also. First of thing, we eliminate xi like we did in the sure complement, but now we perform p eliminations. The system, the other thing with that partition looks like this, where we can have these equations for xi, this first, the second, in pp. You get this form of equations, where for writing this like this, we consider W0 xi 0 and xp xip like 0, just for writing down mathematically. Then we eliminate xi and obtain ai minus 1 times bi minus. This is essentially a linear system with ai. Okay. With this, we substitute, we do like in the sure complement, we substitute xi in the other equations, the remaining equations that have beta 1, beta 2, and so on. And to avoid some too short the notation, we can introduce also these variables beta I bar, that's ai minus 1, beta I, that's a thing that appears here, and here, and here. We will just write down this other notation so that we can simplify the system. then xi will be beta I bar minus w omega I minus 1 bar psi I minus 1 minus theta I xi bar. Where here we consider also w0 bar psi 0 equals 0, as well theta p bar psi p. Okay. Well, introducing this in the other equations, that is these other ones here, beta 1, beta 2, and beta p minus 1, we get the system where psi I is no longer here. We have as variable only xi minus 1, xi, and so on. Rearranging the terms, we get this linear system where we also considering psi 0 and psi p equals 0. Okay? Because they are not in the system before. So we get this final system for xi. This is the smaller linear system. If you do like 100 partitions, you will get a linear system same by 100 by 100 here. That you can solve fast and well. And it is also 3 diagonal by blocks. C lambda 1, lambda 2, and so on. Phi 1, phi 2, they are block k by k. One thing that is important is the following. I present the pseudocode. We'll partition the matrix A into AI. This AI can be decomposed into blocks. One possibility is can decompose using LU. But you can do it in parallel. You can do P factorizations in parallel. Okay? Then you can also compute, since you, after performing this LU computation of the submatrix AI, you can compute B1, Bi, theta I, and omega I on these equations in parallel also. These computations can be performed in parallel. After that, you can compute the blocks of the matrix. These blocks here are the components of this matrix here. You can compute these terms in parallel also. This computation, this one, this one, this one, they are computed in parallel. After that, you can decompose in LU the system of here and then solve. Or you can also solve, I forget to mention this equation here, but the system in psi can be solved here. This is easier to solve and fast. Then you can recover xi in parallel also. This xi, after solving psi here, you can solve this in parallel. The vectors xi and xi are stored adequately in X, and you get this equation. This scales well. Of course, if you use like the proposal here is to use multi-cores computers, because you can perform this implementation easier. But you can use also MPI. I will present some timings. I could not have some. The proposal was to perform some simulations in a computer that we recently acquired that was 64 cores, but we could not turn on the university. We were not able to turn on and make the simulations. I will present the result for these equations that I presented earlier, that's the Euler equation with relaxation term. With this, we performed the computation in a computer with 12 cores in a 64-bit computer. We get, if you use serial computations, that if you do use LU with we get 4 minutes and 24 seconds, but if you get the maximum, that's 12 threads or divisions, in the matrix we get 2 minutes and 28 seconds. If you get a computer with more cores, we get much very good results also, as we could observe. We increased also the mesh and get a computational time also scaling in a half time with 12 cores. So we hope with 64 cores we get much faster computations. We did it with we are now making it available as a library, the solver for this solver for 3 diagonal blocks systems into a library we named TribSys. That's a name that Ismael gave. It's a undergrad student that worked on the implementation of the library. And it was implemented using OpenMP. That's a library to make parallel codes for multi-core machines. This version uses the Intel C compiler and the LAPACK that's available in the library MKL. That's a math kernel library of LAPACK. We will make it available for other compilers like GCC. The GCC compiler, the only problem is that we have to implement, make LAPACK be called correctly. In the MKL library, you have a parsing. I don't know exactly the name, but they have a conversion C to Fortran well made, because in C you store matrix in a way, and in Fortran you store in another way. So you need to perform this conversion, but in the MKL library it's well done. The main routine is a resolve 3 parallel that gets 3 vectors with the matrix. The matrix is the dimension of the matrices, the right-hand side, the dimension of blocks, and the size of partitions. You give essentially you give the matrix, the right-hand side, the dimension of blocks, and the size of partition, and the library performs the solution to you. To get the library, actually, at this moment, you can contact me or Ismael, and the library is already packaged in a single file, in a tar.gz file. I'd like to thank to Dan, Faprej, and Abel for some discussions, and Faprej for the fellowship for Ismael. And I would like to thank the audience.